All right, recording is rolling. I just want to grab these last 5 minutes because my last class ran out of time, right? So free body diagram, there's rocket, deep space, right? No forces. There's air, hockey puck, constant velocity. All right, so there's forces there, right? All right, now I'm pulling a block at constant velocity. Because anytime you see constant velocity, what is the net force every time? 0, because there's 0 acceleration. Now here there's 4 forces, but notice they all zero out, 2 horizontals, 2 verticals, right? And the coefficient of friction for this case is the ratio of friction force to normal force. This was one of your labs. You guys remember coefficient of friction is a material property. Once you know what materials you're working with, it's determinable what the coefficient of friction is, therefore what the ratio of these 2 forces, friction and normal force is. Right? Also, there's 2 kinds of coefficient of friction, kinetic and static. And notice that static is always more than kinetic. What that effectively means is that it takes more force to break the initial friction than it does to keep two objects sliding past each other. Okay, okay, lab table. Car brakes to a stop. This is a scenario that's come up in different contexts in different units. So here is the dynamics version of this. I might ask, what rate can the car slow down? What's its acceleration slowing down? Maybe I should tag on a negative sign to that answer. Okay. I start with Newton's second law of motion, do some substitutions, and I get the rate the car can slow down, that's acceleration, is equal to coefficient of friction times gravity field. Notice what is not in that expression. Initial velocity is not, but also the mass of the car is not. I have mass here, but it ended up canceling out. Hold on to the idea that ends up coming back later. Also, there could be an extension question on this. How far does the car brake to stop? Now, you could take that acceleration and jump back to kinematic motion and answer the question. But you might also remember that later on, when we got to energy and energy conservation, you could answer that from a different point of view, something to do with like kinetic energy and work done by friction. But you get the same answer. Braking distance ends up being independent of the mass of the car. Braking distance also ends up being proportional to the square of the initial speed of the car. Right, right, so that's all extension. Plane velocity. I see 4 forces: thrust, drag, weight, lift. Do you guys see constant velocity means 0 net force? Guys, if you were inside that plane right there, would you feel identical to sitting inside this room? In fact, if you were blindfolded, you wouldn't know if you were inside the plane, if you're inside this room, other than lack of foot space. Here, how about free fall? So we're dropping something off a cliff. Now, true free fall means there's only one force, its own weight. Oftentimes in this class, we ignore air drag. So there you go. But what if you included air drag? Well, now we get the second and third picture. In fact, as long as it's accelerating, that means air drag is also picking up because drag is proportional to v squared. And that'll continue until it reaches terminal velocity. At that point, the force is balanced and it goes down at constant speed. Maybe it's moving really fast, but it's not accelerating anymore. Right. Here's drag force proportional to v squared. Boom, there you go. Here's coefficients of drag. It's a bit beyond the scope of this class, but want you to know there. Oh, here's a pretty good graph. Velocity versus time for considering air drag. Now it starts off, if there's no air drag, it's just a linear relationship. But that's not going to last with air drag. It'll eventually taper off to asymptotically approach terminal velocity. So it's going to kind of curve down like that, right? That was inner notes from a few months ago, right? Let's do block in equilibrium on an incline. I see 3 forces: the green weight, the blue normal force, the red friction force. Now I took the green weight and I split it into components that are parallel and perpendicular to the surface. You guys see that? Just like I told you guys to. We've done this many times, right? Now, those forces are all balanced. They all zero out. Notice that this green component balances with that red friction. This green component balances with this blue normal force. So 0 net force. Now, is the block at rest or is it sliding at constant velocity? Well, if all you have is the free body diagram, you don't know. It's ambiguous. It might be either one of those. Those are physically identical. Right, unless it, okay. They're both 0 net force and 0 acceleration. As you increase the angle, the normal force changes in g cosine theta. Right, there you go. Right. How about different kind of inclines? You know what? I think we got about 10 seconds to the bell. So we're going to pause right there. This is our pause point. We'll continue this on Monday, and then we'll review all next week. But you guys have a great weekend.